Welcome back. For our last week, what we're going to talk about is nuclear magnetic resonance, or NMR. I hope you have all been able to see the lecture on Wednesday if you weren't here, even if you were, to refresh, because we're going to move pretty quickly. But I think you're going to see that it's a lot of fun, because what NMR allows us to do is it allows us to understand how structures are determined at the molecular level. And it's going to start with a lot of physics. We already did, but it gets into some very practical things. So all I can say is bear with me as we go through the physics. It'll all make sense. But I want to start with something that may or may not resonate with you right now. As you know, we released the third midterm scores. You guys did great. I thought you did very well. The average was right around 78. And I know that this can be very daunting. And some of you may feel like this. This comes from a movie. Do you remember the movie The Perfect Storm? Most people your age have not seen it. But as you can see, it can feel a little bit overwhelming. So at this moment, as you're thinking about the final and as it's coming up, who feels like they kind of feel like that picture? Okay. Please do not give up hope, because I want to point something out. There's only one thing wrong about this picture. It's not that there's a wave. What's the only thing wrong with this picture from the point of view of the people in that fishing boat?
Trying to go in this direction instead of that direction.
It's the wrong direction. That's the only thing that's wrong, because what I'd like for you to do is I'd like for you to switch that and realize that if you're feeling like this isn't working for you, switch direction. And I mean do a 180. And that's the best advice I can ever give, because you have plenty of time between now and the final. You have 2 weeks. Now, might seem a little abstract, but I wanted to provide a little bit of clarity to that, because if you're headed the wrong way on that wave, what you need is you need a better surfboard. And what that surfboard is built on, it's built on understanding. And so this is not a comprehensive list, but this is a list of items that you should be very, very familiar with. And if you get these, and you get these ideas down, you'll be able to sit on that board and surf that wave in a way that will absolutely surprise you. So if this has not happened, if you have not caught the wave yet, you feel like you're on the wave going the wrong way in that fishing boat, do not give up. Because if you keep thinking through, look on this list, it's not entirely comprehensive, so there's more to the class than that. But if you go through those items and you understand them, everything should start coming together, not maybe today, but by the time you get ready for the final. To make this point, here's what we're going to do. So it turns out that I don't care when this happens. I don't care if it happened after the first midterm or whether it happens the day before the final. All I want is I want you to understand and learn the material. So here's what we're going to do. We're going to make it automatic. You don't have to do a thing. If the score you get on the final is higher than your lowest midterm that counts, we'll replace that midterm with the score on the final. Well, that's because I want you to experience this and understand what I'm saying. So yes, that's true. That means only one midterm would count, then your final would count as the final plus the midterm, but only if it's in your benefit. So there's no jeopardy here. Only if that's in your benefit, we will do that. We'll do it automatically. Okay. here we are. Here we are. Here's a handout that described a lot of the physics behind NMR. Now, I assume you've been through most of that, and we talked about most of that on Wednesday before Thanksgiving break. And so what I want to do now is I want to start with a way to sort of get you back engaged. I mean, who had a great week, by the way? Yeah, I did too, actually. It was fantastic. So I'm kind of getting it. I want to get you back. So what we're going to do is a quiz you don't turn in. And I want you to go to the next page, which has blanks. And I want you to spend a moment, and either on your tablet computer or with a pen, try to write in the blanks. These are not phrased exactly the same, but these are the same fundamental concepts that we're going to use to build up our physics understanding of NMR, so we can therefore use it in a way that'll be very helpful. So go ahead and you can talk among yourselves. I'm going to spend 5 minutes here. Try to fill this in and see what you get. Okay. We're going to fill this in together, but I'm going to ask you to come up with some guesses here. And again, working on re-engaging. Okay. Certain nuclei, such as hydrogen nuclei, have a quantum mechanical property called spin. Love it. That comes with an associated, correct, magnetic field. So the spin is a quantum mechanical property. There is no analog that I can point to that is visible in our macroscopic world, but it is it's a quantum mechanical property that has associated with it a magnetic field. The hydrogen nuclei can exist in two different, and the story is spin states. The key idea behind quantum mechanics in general is that matter exists in certain states but not others. And so it turns out that a spin of 1/2 is a designation that tells you it can only exist in two different states. Spin plus 1/2, spin minus 1/2. Because spin has an associated magnetic field, in a strong magnetic field, the nuclei with spin line up because, and remember, we're talking nucleus now, the nuclei line up as either plus 1/2 or minus 1/2. They can either be with or opposed to the field, but nothing in between. And that's if we add a really strong magnetic field in the laboratory to a sample. The nuclei line up in that strong magnetic field. Okay, nuclei in the plus 1/2 or minus 1/2 are lower energy. So it's either plus 1/2 or minus 1/2, which is going to be? Exactly, plus 1/2. Nuclei in the plus 1/2 spin state are lower in energy, and the nuclei in the minus 1/2 spin state are of higher energy in a magnetic field. But in that strong magnetic field, they can't be anywhere else. They've got to be aligned with or aligned against. So spins can either be plus 1/2 or minus 1/2 in a strong magnetic field, and they line up with or against. The difference in energy between the plus 1/2 and minus 1/2 spin states is what? And this is the key to the whole thing. That difference in energy changes with magnetic field strength. The stronger the magnetic field strength, the bigger the difference in energy between the plus 1/2 and the minus 1/2 spin states. So, and this is the key to the whole thing. This is what makes it useful to us. Okay, I want you to look at that sentence. Question?
How did we derive an equation where we could figure out that a spin state that we made up basically is directly proportional to something that we can visibly see though?
So most of quantum mechanics is reverse engineering an observation with an equation that correctly explains the magnitude of the observable, but it doesn't provide insight as to what it means. So you might notice I am being very careful how I'm parsing words. So I talk about how the spin comes with an associated magnetic field. We don't really know what or why. We don't really know what spin is. But we know that we can interpret it based on an associated magnetic field. We know that in a strong external magnetic field, it's going to line up with and against. And we know the energy difference between the plus 1/2 and minus 1/2 spin states are directly proportional to the magnetic field. And you notice the important word here, experienced by the hydrogen atom. That's going to be the key to the whole thing. That's why this is useful. That's why this is not just a theoretical physics discussion. We're going to do something very practical with it. This is the part that I don't think you could have figured out ahead of time. But what it turns out So you've got these two spin states, plus 1/2, minus 1/2. It turns out if you give exactly the right amount of energy, the energy difference between the two, you can take the plus 1/2, they'll absorb that energy and flip their spin. And it turns out, for the magnetic fields we use in the laboratory, which are incredibly strong, by the way, it takes a big magnetic field to do this. That energy gap corresponds to radio frequency in the electromagnetic spectrum. So it's radio frequency, electromagnetic radiation that causes the plus 1/2 to flip to the minus 1/2. Okay. Because the energy is absorbed by the plus 1/2 spin state nuclei, causing them to, and we usually talk about it as flip to the minus 1/2 spin state. This is a process we call resonance. So that's the story. What we're going to be doing in the NMR experiment is we're going to be putting our sample in a strong magnetic field. And when we put the sample in a strong magnetic field, we've got plus 1/2 spin states. And what we do is throw in electromagnetic energy of exactly the right strength, energy, that flips the spins to minus. That's the experiment. And that process is called resonance. When the energy is absorbed and the spin flips, that's referred to as resonance. And that's why this technique is referred to as nuclear, because it's the atomic nuclei that were involved, because it's their spins, the nuclear spin that we care about, the quantum mechanical property of spin for those nuclei. We do it in a magnetic field, so it's nuclear magnetic, and the actual experiment is called resonance because we're absorbing energy as we flip those nuclear spins. And that's why this is called NMR, or nuclear magnetic resonance. Okay, this is all review. This is what we did Wednesday. That's why I'm going through it real quick. So far, this is not interesting. This is, unless you're really into physics, which is cool, but it's not interesting from a practical sense. We're about to make it get a lot more interesting. So it turns out, and I want to just call this out. I've said it, but I want to call it out. You can't add more energy and have a spin flip. You can't have less energy and have a spin flip. The whole story behind quantum mechanics is everything is quantized. It has to be exact. So to be useful, it turns out that you have to absorb only the exact right amount of energy to flip the spin. Again, too much energy doesn't work. Not enough doesn't work. It's got to be exactly the right energy. So that's a key idea I want to get across. That means we know that when we see energy absorbed, that energy corresponds to exactly the energy difference between the plus 1/2 and minus 1/2 spin states. Okay. Any questions about that? In the NMR experiments, that's exactly what we do. We monitor which energies are absorbed. Therefore, we know that there are nuclei that have the energy gap between their spin states corresponding to what's absorbed. But as I've described this, this is not interesting yet from a chemical point of view. Because what if every hydrogen atom in the molecule absorbed at the exact same place? Frankly, not useful. So it turns out that's not true. It turns out pretty soon you're going to be able to look at a molecule and you're going to predict which different nuclei absorb at different amounts of energy because of this property called shielding. So this is just where we left off. This is the weird part. Go back to the very first statement that underlies all of this. That is that moving charge creates a magnetic field. If electrons are moving in a spiral, they create a magnetic field. That's what electromagnets are all about. On the other hand, and most people knew that, what a lot of people didn't know was that if you put a charge in a moving magnetic field, flip it, it turns out that induces motion in the charge. So it turns out moving charge creates a magnetic field. The magnetic field that's moving can create charges to move. It'll cause charges to move. So now we have to think about electrons. So now we have electron density, these three-dimensional waves surrounding the nuclei and all of our molecules. And it turns out when we throw those molecules in a very strong laboratory magnetic field, that induces motion. And you're going to learn in physics that there's a directionality to this. It's called the right-hand rule. You'll learn about that. Who's learned about the right-hand rule? Yeah, okay, you know what I'm talking about. So it all moves in the same direction. So that means if we have a lot of electron density around a given nucleus, there's going to be more electron density, which is charged, moving. And it just so happens, this was the part that I had real trouble with. It seemed too coincidental to be true, but it is. Based on that right-hand rule, if you put electron density into a magnetic field, it's induced to move. But what does moving charge create? Its own magnetic field. So you've got this really interesting effect, that you've got the magnetic field causing the electron density to move. That moving electron density causes its own magnetic field. And because of the directionality, the induced magnetic field always directly opposes the laboratory magnetic field. That's the big story. So it turns out if you have more electron density, you get more electron density that is inducing a larger magnetic field, but it's opposite of the magnetic field of the laboratory. So that's what we have. So we have our external magnetic field, and then electron density creates its own magnetic field that is opposite. So if you go back to what we just did at the beginning, and I talked about how the magnetic field experienced by the nucleus, that's because a given nucleus is feeling the magnetic field of the laboratory minus the magnetic field created in opposition to that by the electron density. That's why it's called shielding. The electron density shields the nucleus from the external magnetic field. Are people with me? This is the key concept. So guess what? More electron density around a nucleus, more shielding. Less electron density around a nucleus, less shielding. Therefore, if we know where electron density is in a molecule, we can predict these differences. And we can see those differences. That's the big story, the key to NMR. All right. Any questions about this plot? This is where we left off Wednesday. Let's dive in. Shielding bottom line. Just reiterating this. More electron density generates a larger opposing magnetic field. So a nucleus under more electron density experiences, and this is where you have to get used to this, a smaller magnetic field. More electron density, more shielding, means the nucleus underneath feels less because it was shielded more. There's an inverse relationship. That's going to come back because we're going to make this even harder. But does that make sense? Another way of saying this, more electron density provides more shielding of the external magnetic field. Because, again, this magnetic field is proportional to the electron density, and that's opposed to the overall magnetic field of the laboratory. And so more electron density, we move that direction. That means what this feels is less with more electron density. Any questions about that? There's that inverse relationship. Okay. All right. Now I have to apologize on behalf of all chemists. We plot this backwards. I don't know how to say it any other way. I want you, before we go into this, I want you to look at this and realize the larger number is to the left. Honest to goodness, this has to do with the fact that the very, very first machines that were made used an analog plotter that was measuring things in real time, and that was the direction it went. And so people established all the parameters associated with NMR based on that very first set of machines, and so we were stuck plotting it backwards. So it turns out the larger number is to the left. But let's talk about what this all means. So I just want to say this right now. This causes a lot of confusion. So I want to say it right off the top. I'm going to come back to this. I wanted to say that real quick because I want that to be there. So let's look here. In the classic proton NMR experiment, the molecule of interest is placed in solvent. The solvent has deuterium atoms in place of hydrogen atoms. So that way the solvents don't show up. Deuterium doesn't have spin 1/2. It's invisible to this experiment. It's put in a spinning tube in a very strong magnetic field. The sample is exposed to radio frequency irradiation, and if that irradiation is exactly the right frequency, the energy is absorbed and spins flip from from plus 1/2 to minus 1/2. In other words, they come into resonance. The absorbed energy is plotted in the spectrum. Okay, all spectra are recorded as chemical. So that's the experiment. We're going to scan energy, and if it absorbs, we're going to know where that energy was, and that's going to be characteristic of hydrogens with a given amount of electron density around them. So we're going to correlate that to structure. Of course, it gets better than that, but that's what we do. Now I have to explain the other weird thing about that plot. We plot things in terms of chemical shift. Believe it or not, instead of plotting at energy or frequency that you might expect, those kind of values, we plot this as parts per million. I had trouble with this when I was a student, but basically it's this. That shielding effect comes down to about somewhere between 1 and 10 millionths of the external magnetic field. So there is an effect, but it's always about 1 to 10 millionths of how big the external field was. So what we're going to plot is the difference between no electron density and we get up to about 10 parts per million. And that way, and this is something we'll come back to later, but I'll just say it right now. That way, if we have different magnetic fields, as we got better and better at making magnets, it turned out that the energy difference changed, but not compared to the external magnetic field. So it's a ratio. How much the chemical shift is away from zero. We're going to talk about zero. And that is going to scale proportionally as parts per million, no matter your magnet size. That's why we do a ratio. So you have a magnet that's twice as strong, it's still the same number of parts per million. So that's why we do it that way. But that's why the scale is called parts per million. Okay. We're not done. It was chosen that tetramethylsilane, so a silicon atom with 4 methyl groups, is placed on the sample and in the sample because it's unreactive, and it's assigned 0 parts per million. We're going to see why that's so critical. So everything that we're going to do is going to be related to that signal for TMS. We're going to call that 0. That way, everybody's NMR machine, no matter how strong the magnet, will always be plotting the exact same values. Okay. Any questions about that? We call the chemical shift delta, by the way, just because if you're in science, you have to name it after a Greek letter because people think you're smart when you say that. I'm not kidding. All right, here we go. So now you know why this is chemical shift, and now you know why that's parts per million. There is a terminology people use. Downfield corresponds to less shielding around a nucleus. So here's the part that is really interesting. Again, it's because this is backwards. On this plot, more electron density is to the right. Less electron density is to the left. More electron density means we have more shielding. When there's less electron density, we call it de-shielding. We have upfield and downfield. If we've got two peaks, if it's toward TMS, we call it upfield. If it's farther from TMS or the 0, we call it downfield. Those are terms you'll see. But then also, the more electron density, the more shielding we have. And it makes sense that those values are going to be smaller. Because remember, the shielding, more electron density, creates a larger magnetic field that opposes the external one. So we move toward TMS, we move that direction with more electron density around your hydrogens. And just to put this in context, I'm saying everything that we've already talked about, but I want to put it in one place. What you're going to get used to looking at, between 1 and 10 is the useful range in terms of parts per million. You now know why parts per million is used. That's the chemical shift. And the closer to 0, the more electron density, because the more shielding there is. The closer to 10, the less electron density around that hydrogen, the less shielding. In other words, it's de-shielded. Okay, that's the terminology. Turns out, any questions about that? So we're just setting the stage. I do want to remind you, this dang scale is bass-backwards. Larger numbers are to the left. Again, that's a historical artifact, which is unfortunate. Okay, the hybridization state of atoms attached influences shielding in predictable ways by removing different amounts of electron density around adjacent nuclei. Electron density in pi bonds also has a large effect because pi electrons are more free to circulate in a magnetic field compared to sigma bonds. These are both quantum mechanical. Frankly, we're not going to ask you to predict this based on first principles, but there's the concept. Pi bonds do wacky things, and hybridization has a big effect. That's what we want you to remember. So what we're going to start looking at is tables. So you're going to be given always these tables of chemical shifts. If you look at the old finals, you'll notice, yeah, we give you the tables. But what I'm saying is, with these parameters, the amount of electron density, any adjacent pi bonds, and hybridization state, you put those three things together, and you can start seeing big differences in where different hydrogens come, and it's very characteristic. So we can start looking at functional groups, and we could know where on that scale of 0 to 10, we can tell where something is going to appear based on those three parameters. Electron density, hybridization state, are there any pi bonds around? And so we accumulate these into tables. If you have an sp3 carbon, and you've got hydrogens on it, they come around 0.8 to 1.7. If there's a pi bond nearby, it moves to 1.6 to 2.6. If it's a sp hybridized, we're going to jump over here. If it's hanging out on, not near the pi bond, but on an sp2, we're going to jump all the way to 4.6, 5.7. Don't worry about the inconsistency there. You think, wait, if it goes from a single bond, so sp3 to sp2, you go from like 1-ish to 5-ish. How come a triple bond or an sp isn't farther? Quantum mechanics, math, don't worry about it. You just kind of got to get used to that. And then if we put them together, this hydrogen, we've got a pi bond on an sp2, it goes all the way down to 9.5. We don't expect you to predict that at all. Just look them up in the tables. It all has to do with electron density and everything that I said qualitatively, but you're not responsible for it. It's heavy-duty math. In fact, here's a complete table. You will be given this on your final, this exact table. Question? So R just means any alkyl group, and it doesn't matter which one. So it just means it could be methyl, it could be ethyl, it could be propyl. We don't care. So that's the point. This is trying to be very generic because you look for these different functional groups and you'll identify those different hydrogens in those patterns, but then we don't worry about it other than that. Okay. Now some people like what's at the bottom better. The information is identical. Whether you like tables of numbers, which tell you where on the plot things are going to come, so then you go look on the table, you go look on the plot, that's one way to look at it. Other people like to look at the actual C0, and we go all the way out to higher numbers like 13. You're not going to have to worry about that. Most of it's going to be constrained down in here. But the values are the same. So, for example, if we're looking at a methyl group, notice it's between 0.8 and 1.0. Here is that same methyl group. It's between 0.8 and 1.0. So that information is the same. It's just plotted where you might find those different hydrogens down on the bottom, but it's in tabular form, and we're going to give you both. Some people prefer one or the other. But the point is this. Amount of electron density, hybridization state, the adjacent presence or absence of a pi bond predict that different functional groups, the hydrogens in those different functional groups, come at very different places. And that has to do with that energy gap between plus 1/2 and minus 1/2. And again, in the experiment, we scan all wavelengths. And if the energy matches, that's absorbed. And we plot that as ppm. And so the presence or absence of those different kinds of hydrogens are indicated on our plot. You with me? Okay. That's a piece of it. That's a huge piece of it. Let's get serious. All right. We're actually going to look at one. The big question that comes about that is different than the way you've been thinking before is you have to think about equivalence. And it turns out that equivalence is a big story with NMR. What does this mean? Chemically equivalent hydrogen atoms give rise to the same signal. If a hydrogen atom in a molecule is in the exact same environment, so all those parameters, electron density, hybridization state, adjacent pi bonds, all of that is identical, then you're going to get hydrogens that absorb exactly the same. This is because sp3, freely rotating atoms, are going to rotate so fast that all of those hydrogens are experiencing the exact same environment. So let me draw a molecule for you. Okay. In this molecule, when we look at it, the three hydrogens on the left are all equivalent. Because that bond is freely rotating. So those three hydrogens are going to give rise to the exact same signal. They're not different. On the other hand, we look over here and we have this methyl group. And again, we have free bond rotation around that bond. All of those hydrogens are equivalent. So even though this molecule has 6 different hydrogen atoms, how many signals is it going to give rise to? Just 2. Here is the actual spectrum, the NMR spectrum of that molecule. Remembering that that direction is less electron density. What I want you to do for me is you can use the table or you can use your intuition. Either one is fine with me. I want you to think through and predict this signal right here around 3.75. Less electron density. Is that going to be associated with what I've labeled red or blue? So go ahead and look on the charts that we have right above there and tell me which one that's going to be. Is it going to be what I labeled in red or blue? The one at 3.75. Look on the chart. That is the hydrogen we're talking about. Look where it comes. Just to be sure about that, if we are looking at something that is adjacent, where'd it go? Where'd it go? Adjacent to this, it comes in the 2.2 On the other side, it comes in the 2.2 to 2.6 range. So what this means is that if I call this A and I call this B, A is going to be right here, and the signal for B is going to be near 2. That's how you interpret NMR spectra. Individual signals, you now know they represent 3 hydrogens each. But now you can predict, based on what's in the chart, you can predict what you're going to see. Because what's below is an actual measurement. That was an actual NMR spectrum. And congratulations, you've just interpreted your first NMR spectrum. Yay! Yay! Okay. Next point. The area of an HNMR signal is proportional to the number of equivalent H atoms that give rise to that signal. So let's draw a different molecule. Now this is a tougher question. Okay, take a look at this molecule. This is where equivalent hydrogens gets weird. Based on what we just said, it should be very clear that these 3 are equivalent. But it turns out all 9 of these are equivalent. Symmetry. All of those bonds rotate, so all those hydrogen atoms experience exactly the same environment. That's a tough concept. You might have to think about it for a while. But all 9 of those I circled in red are equivalent. Their relationship to every other atom in the molecule is the same. All 9 of those. If you looked on the sheet, you would find out that because now these hydrogens are 1 atom farther away from that oxygen, they're going to come at around 1.5. But notice the signal for B, and they always give you the integration, is 67, versus the signal for A, the area under that peak. You can't just eyeball it, and peak height is sometimes deceptive, because short fat can be a lot of signal. Tall, thin can be not very much. So you go based on, we will always give that to you, that number. It's measured by the machine. This is going to be A. So 23 versus 67, 3 to 1. So now we get more information. So now we know where it comes, tells us what it is in terms of functional group, and we now know the area under the signal corresponds to the number of hydrogen atoms it represents. We're building up our information. Okay. Any questions about that? This is the last big thing we're going to do today. And so I'm going to throw a monkey wrench into your understanding of this process. But kind of get what we're doing? We're absorbing energy, we flip a spin. Where it comes tells us what functional group it is. The size, the area, tells us how many equivalent hydrogens are there, but now we have to get weird. Surprising fact, the absolute energy between the hydrogen nuclei and a +1 and -1 spin state, it's real, and that's what we're measuring, but it is, on the grand scheme of things, so small that the Boltzmann distribution, which tells us how different energy states are going to be distributed at a given temperature. Who's heard of the Boltzmann equation? Okay, not that many of you. Don't worry about it. There's an equation that says this. All I want you to take away from this is a surprising fact. You might have thought that you put a molecule in a very strong magnetic field, all the hydrogens are +1/2 because that's the lower energy state. Turns out that's not true. Turns out it's about 50-50 because this difference in energy on the grand scheme of things is so small. Yeah, there's always more in the +1/2, but not by a whole lot. That's the weirdness. Okay, sorry about that, but you got to get over that. So it's something I just had to accept. So I just got to tell you. In a given molecule, a given hydrogen atom can be +1/2, -1/2. We throw it in a strong magnetic field. We do get more in the lower energy state, and those are the ones we monitor as they flip, come into resonance. But it's about 1 to 1. It's like 99 to 100. You know, it's not very much different. You just have to recognize that. Okay. Let's make some sense out of that. This is where life gets very interesting. So, spins, nuclear spins, have an associated magnetic field. Turns out +1/2 and -1/2 spin states are different. Now I have to define something for you. I'm going to talk about something called adjacent, and I'm referring to something that's no more than 3 bonds away. You'll see why that matters. Okay. Take a breath. Here we go. This is the last big thing. The last big thing. Adjacent nuclei have magnetic fields associated with their spins. The spins of equivalent adjacent nuclei can be either +1/2 or -1/2, and at room temperature, they are found in about a 50-50 mixture at any given nucleus. Very slight excess of the lower energy +1/2. We've talked about that. These can add to give n+1 different spin combinations in proportion predicted by Pascal's triangle. Each different spin combination produces a different magnetic field, which leads to n+1 splittings in the peaks of the NMR spectra of the adjacent, no more than 3 bonds away nuclei. Who has any clue what that means? Okay, we're going to get there. We're going to get there. Okay. I've got a molecule that only has 2 hydrogens. Here's the point. We've got an external magnetic field that comes along and it goes this way. Notice I've got chlorines versus fluorines. which of those, HA or HB, is going to have more electron density? HA or HB? Given chlorines versus fluorines, what we're worried about here is the inductive effect. Fluorine is more electronegative. So does HA or HB have more electron density? Who says HB? Exactly, because chlorine is less electronegative. So it turns out, if it has more electron density, it has more shielding. But now, here's the big thing. Watch this. Okay, that gets me to there. Oops. Here we go. So the last thing I'm going to say today, it's so cool. That's kind of ugly, but we'll go with it. HA is 1, 2, 3 bonds away. That's adjacent. It turns out that HB not only feels the full external magnetic field, it also feels the shielding. There's more electron density around HB because it's got chlorines, not fluorines. But HA could either be plus 1/2 or minus 1/2, about 50-50, and that matters. So there's 3 components. So it turns out instead of 1 signal for HB, we get 2. Does that make sense? Okay, and then we do the same thing over here. And this is exactly where I wanted to get to today. Okay. I'm going to leave it there because I don't expect that that's absorbed. But it turns out we have something extraordinarily important to talk about. Now, first thing, tomorrow, office hour, I'm going to go through this again. I'm also going to be going through how I think you should be preparing for the final. And it'll be a great time. But let me just summarize very quickly where we've been. It's not as hard as you think. Number 1, the overall chemical shift is determined by the functional group because it's dependent on amount of electron density, hybridization state, and if there's a pi bond around. But you can look those up in tables. What I'm now telling you is that the number of equivalent hydrogens is proportional to the size of the signal, so you can tell how many hydrogens. What we're going to do with this is now you can tell who is next to whom. Because if you're 3 bonds away, you split the signal. And you split it in characteristic ways. So there's 3 components: the external magnetic field, the shielding, and the other effects, and now the splitting. We're going to get there. But I want to talk about something very important. I have spent a lot of time getting you motivated when it comes to, I hope, taking care of your own mental and physical health with exercise. Well, it turns out, as future physicians or those of you who are going into the medical profession, there's something I want you to hear. I don't know how well this is addressed in different levels of medical education. But there is something even more important going on that's relevant. And that has to do with the effect on the healing process of strenuous physical exercise. So I want to show you something that is just now coming to light. It turns out there's chemotherapy, there's radiation, there's a lot of things. But our immune systems are activated if, in fact, we go through strenuous exercise. I'm not going to take you through the immunology here, but there is firm scientific evidence that that's true. Beyond the physical scientific evidence, wake up, computer, hold on. Okay. Turns out, I want to show you something quite remarkable. So, turns out there's a person from the state of Texas, his name is Iram Leon, who won a marathon pushing his 7-year-old daughter. I'm going to let that land for a minute. He was pushing his daughter in a marathon, but this is not why he became an international news story. He became an international news story because not only did he win a marathon in about 3 hours pushing his daughter, but in fact, he has a terminal brain tumor. In fact, he's right here. Come on, Iram. Just tell your story. Keep it clean. Keep it clean. Don't give me that score. Start falling for that score. You're going to do this right, right?
How y'all doing? So y'all, I've been running my whole life. You know, people ask me when I started running, same time y'all did, right after I started walking. You know, you try to go a little faster, I just haven't stopped. But I grew up in Mexico, and out there our schools are outside, at least where I'm from. And when I came to the U.S., out there I'd run from place to place, and in the U.S. I was trying to run in the hallways of a little school. I got sent to the principal's office when I was 8 years old. I got spanked. And I learned my lesson because when I went to 7th grade, I got sent to the principal's office and I got spanked for running in the hall. But I kept running. He actually ended up sending me out to run with the track team to show me where I should really run. And then I outran his entire track team, and he's like, would you like to join the track team? So I kept running throughout high school. Throughout college, I joined the cross-country team. And then I graduated college, and I got a little bit lazy, you know. The first couple of years of college, I actually got a little bit lazy. How many of you guys put on the freshman 15? Anybody? You want to admit it? Y'all are slackers. I put on 35 pounds. I went to college, and they had those all-you-can-eat buffets, and I made the most of it. So my junior year, I started running again, joined the cross-country team. I got much healthier by my senior year. And then after college, I kept running. I didn't really keep training, but when I was about to get really old, I decided I needed to do a race. I was about to turn 30, you know. I was about to get ancient. Not as old as that guy.
What I was going to say.
I ran a marathon. It went all right. I ended up walking a little bit of it, so I was like, let me try again. And as I was getting into the second cycle of it, shortly after I had turned 30, I was at a restaurant, and I woke up and next to, say, EMTs, because I had a seizure. They took me to the hospital and this and that, and because it was on a Friday afternoon, they weren't going to be able to get to the biopsy till Monday, blah, blah, blah. I asked permission to go running while I was at the hospital. I was supposed to stay on the hospital grounds, just run while a nurse was there, and I was supposed to check in every turn. After a couple of loops, she got bored, and she's like, I had a friend who was an EMT running with me. She was like, okay, well, he's got you. And as soon as she left, we took off and ran a few miles out of the hospital because I had to get out of there. That's not a true story. If you're from my health insurance, I'm totally making that up. But I kept running, and I had the biopsy, and I would find out that biopsy results were supposed to take a couple of days. They took almost 2 weeks. Find out a guy who had never called in sick, that I had brain cancer in my left temporal lobe. And while I was sitting there with all these tests, EKGs, you know, EEGs, MRIs, CAT scans, had me thinking of some other 3 letters. And there you go. And so I just kept running because running was honestly therapeutic. It got to be where I was a little bit away from my problems, or at least beside them for a few miles. I had trained for my second marathon. I was trying to cancel it all in light of the medical treatments, but I realized that I needed this as I was sitting through all these tests. And so I had a race coming up, the Decker Half Marathon, which is actually this Sunday. And it's one of these where they just give you the next bib. It's not a sign. You know, they just give you the next one when you sign up. And they gave me bib 911. I'm like, man, I don't even have to put the emergency number on the back. You guys put it on the front. And it would be the first race that I would place in since I was in college. And I'm like, all right, not everything goes downhill when you turn 30. So I kept running after all these tests. We did a test where they put parts of my brain to sleep to see how risky the surgery would be. It's called the water test. They went into my groin, went all the way up to my brain, putting parts of it to sleep. That's proving what I've always known since college, that my brain and my groin are connected. It only takes a few seconds for them to communicate, and we know which one puts the other to sleep.
Thanks, Hiram.
Is he shaking his head? 8-hour neuropsychologicals, all kinds of blood work, and finally they were like, there was a high risk of whether or not I'd be able to come out with a surgery. And that test actually couldn't, when they put my language to say, I couldn't even think in words. And I was like, this must be what it's like to be a small child or a dog, where you're still aware, but words aren't even in your brain. So that was the scariest medical moment of my life. And as we did all this, they're finally like, well, it's up to you whether or not you want to do surgery, because these are some of the risks that come with, you know. I thought about it, and I did, and the doctor said, okay, let's do it here in the next couple of weeks. I'm like, well, I've got a marathon in 5 weeks. Can we do it after that? So I put out my brain surgery to do a marathon, and when you don't think you have another one, you end up going pretty hard. And at the time, that was my fastest marathon. The first one I would qualify for Boston on. I had to go through surgery. After that, I had to do some rehab. I was tilting, a little bit of balance. I had to do some neuropsychological rehab. But eventually, I got back to running. And I felt like some of you probably felt. The first time I ran 2 miles after a few months out, I was like, this is why everybody hates this. But I got back to running, and I started running with my daughter. She was 4 at the time I got brain cancer, and I'd never ran with her before, and I started running with her in a stroller. And she'd always like, faster, Daddy, faster. I'm like, this is as fast as I can go. And you know, she was getting older. She was getting a little too big, and I knew that those days weren't going to last too much longer. So I kept trying to find different races that we could do. And for some reason, no marathon would let me in. And finally, the Gusher Marathon out in Beaumont, Texas, let me in. And so we're out there, and we're doing, it's double course. So the half marathoners went once, the marathoners. And there were several people ahead of me. And then when we get to the second loop, there's no one ahead of me for a little while. And so I turned to the bike person that they'd put with us for safety, and I'm like, man, how far back am I? They're like, oh, there's no one in front of you. And I'm like, oh man, pressure's off. And so we kept running. You know, it's a marathon. You end up fading some at the end, and I thought, oh, somebody's going to pass me. When I had about a half mile left, I could see that the finish line, we were coming the other direction. I'm like, I'm going to win a marathon. And I did that marathon 1 second slower than the one I'd put out brain surgery for. Kid slows you down, you know. I kept running. My daughter ran. She would end up joining her cross-country team in middle school and high school, winning some meets in both. I got my mom to run. She's in her 70s, and she did her first half marathon at age 60. But I've kept running because it's therapeutic. But you know, my doctors at Duke, I actually went to Duke for brain surgery, and they sent me a similar test. It might not have been this exact one. Both my local doctors and my Duke doctors, that long-distance runners have a higher brain cancer survival rate. And you know, and oddly enough, that year became the highest mileage year of my life, just coincidentally, right? So I kept running, and this year, my neuro-oncologist, when I went to go see him, he said, I don't know why this hasn't grown on you. He says, you're my second best patient ever. He said, it's like, I'm going to tell you something, but if you tell anybody about this, I'll deny it. So that's why I thought I'd quote it to a couple hundred people. He said, I think something in your immune system may be attacking the tumor in a way that, you know, it's just kind of an emerging theory, but I think that you're one of those. I've had to I've taken quite a few drugs since all this started. Not any of the ones I rejected in college. But so that's messed with some organs, and so I've had to do a variety of things for that this year. The last 3 years I've had some things to do with my liver and my kidney and my bladder, and so we've had to mess with some things. But one of my doctors said literally within the last few weeks or so, like, I think your problems are probably worse, and that all your exercise is masking it. He's like, but we don't want to know the full problem, so don't stop running. I've put off changing drugs or this treatment or that for after a race. And so I was like, let's start just so that it doesn't mess with the race, you know? And so I genuinely think that this is why I've been able to keep going. It's just literally 1 foot in front of the other. You know, if people are like, how do you run? I'm like, 1 foot in front of the other. I'm like, if you keep trying to do the same foot over and over, that's tough. But as long as you do 1 foot and then the other, you're going to be fine. You know, I know I still look 29, but the 10-year survival rate of the cancer I have is 12%. 12%. So out of most people who would have gotten it when I have, most of them would have been dead. But when this all started, my doctor said, you're not going to beat this probably. We're just hoping to get you closer to 40. 3 months ago, I turned 44. A little under a month ago was my 14th cancerversary. And when I think about that, I think back of what an old college professor of mine used to say, you know. I wonder where we're going with this.
No, I'll find it. I'll find it. Keep going. Keep going. You're in here somewhere. Hold on. We'll find you. There he is. There you are.
Yeah. You know, so when I think about that 12%, I remember what an old college professor of mine used to say, that statistics are like bikinis. What they reveal is interesting, but what they conceal is vital. And so I'll tell y'all that I keep running. I've yet to miss a day this year. And the reason I keep running, I want to keep defying those statistics. And I want to look good in a bikini.
You can't go away yet. So I hope you take that to heart, because you know Iram should not be here. And one of the biggest honors that I've ever had was right when he turned 40, because he was told he never would. We went on a run together, and I'll never forget it, because I'm thinking, okay, we'll just do. He's really fast, and I'm not, by the way, so that's a big thing. I thought, okay, I'll survive this. And then I find out he chooses the biggest darn hill in the world to run over.
Mount Bonnell, if you haven't been there.
Yeah, so we do Mount Bonnell and we come back. And so, you know, I survived. But we got back and I said, okay, this was a celebration. Why did you do that? And the answer was, you just turned 40 and we had to.
Because I'm over the hill.
All right. Tuesday is office hours. And Wednesday, we're going to finish NMR and talk about something even more important. And I can't wait to see how things go through the rest of the semester. Thank you, Arm. Thank you.
I had a question about the stuff in the class today. So, maybe I missed this, but like on the HA and HB on this side, why was the B on the, like, what's the story behind the, like, why is it B over here and A over here instead of the other way around?
So B has chlorine on it. Chlorine is less electronegative than fluorine.
Okay.
Fluorine's pulling electron density away.
Oh, because of the flipped. It's the. Okay,
It's the
okay.
flip. It's the darn flip scale.
Yeah. Okay. Okay.
That's what gets everybody.
Okay.
That's why it's the very first thing I said.
yeah,
The
you said
scale
that.
is flipped.
Yeah, and then you said it again, and I was like, oh. I
No,
got
now
it.
see,
got
now
me
you get
already.
it. Okay. Where did iron go?